Good afternoon, everybody. Hope you all enjoyed lunch. I'll get things kicked off. So, just kind of a quick agenda that we're going to go over. So I'm going to begin by going over kind of the group that I'm a part of within Williams. We refer to it as New Energy Ventures, and specifically why New Energy Ventures within Williams is actually looking at evaluating hydrogen. And I'm then going to go into our recent fuel gas blending test at our Kemmerer compressor station in Wyoming that we collaborated on with Cooper. Both Hans and Jordan had a very heavy hand in this project and wouldn't have been possible without either of them, as well as what we're potentially going to be utilizing these results for in the future for other hydrogen projects, as well as some additional considerations that the folks on my team are considering when we're looking at permanent hydrogen blending projects. So to start, just a little bit about New Energy Ventures. So New Energy Ventures was established in 2018, really within Williams to determine a pathway to our net zero commitment by 2050, as well as pursue opportunities in low carbon energy markets to ensure a company like Williams is really able to prosper during this ongoing energy transition. And the team focuses on initiatives to really optimize operational practices to maximize fuel efficiency and reduce unnecessary emissions of all types, as well as source cleaner sources of power. And in addition to the operational improvement side, we're also responsible for developing and executing projects centered around these energy transition markets that I keep referring to, including things like hydrogen, carbon capture, solar and wind, as well as waste heat recovery, that is really going to allow us to both reduce our emissions and create revenue throughout this energy transition. So why hydrogen? Well, the answer is really twofold. So when I talk about hydrogen, I like to refer to hydrogen as just fancy natural gas. Our experience as a reliable operator in the midstream natural gas space really gives us a unique position to excel in this developing hydrogen economy, which is going to require production infrastructure similar to a gas processing plant, of which we own and operate many, as well as pipelines, which, being Williams, is our bread and butter that we've done for the past several decades. And this large infrastructure footprint that we already currently have, again, is able to give us this unique edge to excel in the hydrogen economy, and we are actively evaluating production, transmission, and utilization projects across our entire footprint, as you can see on the screen right here. And second, there is also an opportunity for a company like Williams to act as its own customer and utilize this produced clean hydrogen as a decarbonization mechanism. So, as mentioned earlier, we have a goal to achieve net zero operation by 2050. And as you can see on that pie chart to the right, probably should have picked a better color scheme, but almost 70% of our Scope 1 and Scope 2 emissions came from the combustion of natural gas in our turbines and reciprocating engines. So if we have any shot at meeting this net zero goal, we're going to have to completely address the issue of combustion emissions. And operational improvements such as rewheeling compressors, seal gas recovery, as well as replacing dirtier burning engines with cleaner ones are low-hanging fruit that we are currently in the process of doing, but they're not going to get us all the way. And the way I see it, achieving net zero is going to require a combination of the following. A, replacing natural gas drivers with electric drivers. B, implementing carbon capture, post-combustion carbon capture at all of our compressor stations and gas processing plants. And C, burning non-hydrocarbon fuels such as hydrogen that don't produce CO2 when combusted. And during our internal evaluations, we're really finding that there are certain scenarios where blending hydrogen may in fact be the superior method to reduce combustion emissions when compared to carbon capture as well as EMD replacements. So post-combustion carbon capture, if you're not familiar with it, is very difficult to do due to really the low CO2 concentration in typical flue gas. And it doesn't really matter the method that you use to do it, whether it's amines, temperature swing absorption, or calcification. That low CO2 percentage is really detrimental to your economics as well as efficiency. And electric drivers, they require a lot of power and really must be situated close to high voltage conductors along with a substation. And these are things that typically aren't found at a typical Williams compressor station, which is located in the middle of nowhere. Typically with a lot of times with no actual supplied power. Power is supplied by something like microturbines. And in addition, going full electric may compromise our reliability. So if there's something like a power outage, we're not able to move gas. So there goes our reliability. And hydrogen is really, in certain circumstances, is able to be that happy middle. So there are production methods such as pyrolysis that are able to really produce clean hydrogen with relatively small amounts of power when compared to something like electrolysis, and does not produce CO2, but rather things like carbon black or graphene. And in addition, blue hydrogen production methods such as autothermal or steam methane reforming are able to produce emissions with a much higher concentration of CO2, meaning that carbon capture is more attainable with something like steam methane reforming or autothermal reforming when compared to simple post-combustion carbon capture. And finally, fuel gas blending is not going to compromise reliability. If, say, the hydrogen production infrastructure is down, then these turbines and recips can simply switch over from hydrogen and natural gas blend to a natural gas blend almost instantaneously with no after effects. So about a year and a half ago, Williams was awarded a $1.2 million grant from the Wyoming Energy Association to perform a feasibility study leading to the development of low hydrogen production utilizing our existing assets in the state of Wyoming. And with the recent passage of the IRA, as some of my fellow presenters have alluded to, this concept's really been amped up to 11, and Wyoming is actively positioning itself to really be one of these locations for a clean hydrogen production hub eligible for almost a portion of that $8 billion in federal funding. And this feasibility study that I mentioned really consists of three main parts. The first being a water resource study that's going to evaluate really any sources of water within Wyoming that we could potentially use for hydrogen production. Integrity testing, evaluating both transmission pipe and laterals within Wyoming to determine the effects of hydrogen embrittlement. And the topic that I'm really going to be spending most of this presentation on, which is performing a field test to determine the effects of hydrogen blending on our combustion emissions and stability. So once we ended up deciding on this unit with assistance from Cooper, the unit that we chose was a 2,000 horsepower 6V250 two-stroke engine at our Kemmerer compressor station in Wyoming. Per the terms of the grant, the work had to specifically benefit assets in Wyoming, so we were somewhat limited on our engine choice, and this was the best candidate by far. So really the challenge with this project was how to install a temporary system that would be able to minimize impacts on local operation. And I made a little process flow diagram of how we actually built this thing. So as you can see in the top left corner right here, there was a very conveniently located spool piece on the fuel gas piping that was actually removed and replaced with this bypass valve and two isolation valve assembly right here. So when you close this bypass valve right here, the natural gas fuel gas is able to flow towards the mixer, whereby hydrogen can then be added at the desired concentration by opening up your hydrogen valve, and then the blended product is able to follow this new piping construction back to the discharge side of the bypass valve and towards the engine. And to measure both the hydrogen and the natural gas flows, we included 3 flow meters, one on the natural gas side, one on the hydrogen side, and one on the blended side to verify the blend concentration that we were getting. And along with the process piping in the mixer, with assistance from Cooper, we put in a hyperbalance 4 system. This hyperbalance system is not an auto balancing system. It is simply a pressure monitoring system that we put in each of these 6 cylinders to really be able to continuously record the peak pressure as well as location of peak pressure, which was then connected to our station PLC or control panel, really for ease of monitoring. And our hydrogen supply came from a tube trailer at about 3,000 pounds, was then regulated to 80 pounds again, to ensure that we were within the bounds of the MAOP of our fuel gas piping. And this was verified with some PSDs that we put in, set at 125 pounds, really to ensure proper overpressure protection during the test. And on the emissions side, we brought in what's known as an FTIR trailer that was able to perform continuous emissions monitoring on the pollutants of interest, which really included your CO2, your CO, your total hydrocarbons, volatile organic compounds, as well as NOx. Now, I know this is a compression conference, but one very interesting and kind of key decision we had to make for this test is what pipe we were going to use, what ASME piping standard were we going to use for this project. Whether the two types that we could have used were ASME B31.8 or B31.12, B31.12 being the standard for hydrogen service when concentrations are above 10%. So I ended up issuing a variance from our normal operating procedures to qualify the piping under B31.8 because, as you can see a summary of B31.12, really there's two options for B31.12. You could perform this prescriptive method, which basically requires that you take a 50% pressure cut to your MAOP to ensure that any effects of embrittlement are counteracted. Or option B, which is a testing-based method, which requires you to perform a very complicated and in-depth series of integrity testing to, again, verify the pipe has properties that are able to resist that drop in toughness coming from hydrogen embrittlement. So the reason we ended up going with B31.8 is while hydrogen embrittlement is always going to be a concern, the effects of embrittlement are made much worse for large diameter piping that's really operating at a high percent specified minimum yield strength, or SMICE, that also has large pressure fluctuations. And since the fuel gas piping we used was only 3 inches, was operating at only about 10% SMICE with little pressure fluctuations because it was fuel gas piping, really any effects on the embrittlement side were deemed to be inconsequential. Now, during the test, we did devise numerous safety measures to really minimize the major risks associated with utilization of hydrogen. So hydrogen is not a walk in the park to deal with. It's very tiny, has a much larger explosive range than methane, and also burns much hotter and faster, which could, relatively speaking, increase the risk of leaks as well as unstable combustion that could potentially damage the engine or other equipment in the compressor station. So really, to minimize this risk, the team developed a number of operating procedures designed to really isolate the engine from the rest of the station at the conclusion of each test day, as well as manning the unit controls at all times during any increase or decrease in hydrogen concentration. And second, to minimize the risk of leaks, we took 2 distinct actions. The first was that prior to putting in any hydrogen, we actually leak tested the entire assembly with helium beforehand. And since helium is a smaller molecule than hydrogen, we figured that if the assembly was able to hold helium, which it did, it would then be able to hold hydrogen. Really, as a second method of precaution, we also purchased some portable hydrogen gas detectors, and during operation basically ran these detectors up and down the entire assembly just to verify basically any leak sweeps around potentially vulnerable components. If we ended up detecting a leak, which again we didn't, we had a procedure in place to immediately stop the test, shut down the unit, and ensure that it was isolated from the rest of the station, and the root cause analysis of the leak was identified before moving forward. Getting into the test itself, really what the purpose of this test was is we were basically performing a series of tests at various hydrogen blend percentages that attempted to really obtain an understanding of the effects of your ignition timing, your air manifold pressure, your blend percentage, as well as your engine torque on your combustion emissions and combustion stability. So we began by attempting to perform what we called sweeps, where the ignition timing was set as the independent variable, the air manifold pressure set as the dependent variable, and vice versa from 0 to 20% hydrogen in intervals of 5. However, we ended up finding that the allowable air-fuel ratio could really only be leaned out so much and the ignition timing retarded so far before we started to get some knock, which could be heard as well as viewed in real time via the hyperbalance system we installed, especially for these higher hydrogen blends. We then ended up transitioning over to a torque sweep, where the ignition timing and the air manifold pressure were really kept constant to the best of our ability, and our engine torque and hydrogen percentage adjusted from 70 to 100% and 0 to 30% respectively. And engine torque is proportional to basically your engine load, so your power output of the engine was set between 70 and 100%. So we ended up receiving the highest quality, before I get there, so one thing I forgot to mention is that on the 13th, you might notice that we were able to get up to 30% hydrogen that day. So the test was really only we were only initially going from 0% to 20%, but on the 13th, it ended up being much cooler that day, and we were able to run 20% hydrogen with no issues. So we really decided to push the limits on this test and see if we would be able to get higher, get to 30%, and see what those potential impacts were. And we're very glad we did. During this cooler day, we didn't end up seeing any knock, and we were able to run up to 30% hydrogen with really no issues. It's also glad we did that because we ended up receiving the highest quality data from the torque sweeps that I just mentioned. And these graphs are reflective of really the percent change from 0% hydrogen in emissions going from 0%, 10%, 20%, and 30% at these various engine torques. So your CO2e, or equivalent CO2, which is what we use to, again, calculate emissions, really consisted of mass-based measurements of your CO2, CH4, and N2O, so you're basically your greenhouse gases. Your methane emissions are multiplied by 25 times, and your N2O emissions are multiplied by 298 times, since both of these types of emissions have a much greater global warming potential than your CO2. And as you can see from the graphs over here, at 100% torque at 30% hydrogen, we achieved about a 9% reduction in CO2e, with the majority of these drops coming from basically reductions in CO2 emissions. And this was really because on a mass basis, our CO2 emissions were 100 times greater than our methane emissions and 200,000 times greater than our N2O emissions. Something else I'd like to point out that the Cooper folks already brought up is at the same time, Southern Star, or at a similar time, Southern Star also performed a similar test at one of their compressor stations in Kansas, and while they did get slightly better results than us, mainly due to differences in location, engine type, control methods, really everything that comes from completing a test in the field rather than in the lab, what's really important to see is that the general trends were the same, and that we were able to conclude based on these two tests that adding hydrogen is going to reduce all forms of emissions in reciprocating engines, these older reciprocating engines except for NOx. And, diving a little deeper into the NOx, NOx is going to increase almost instantaneously in reciprocating engines such as these when hydrogen is added due to your higher flame temperatures resultant from hydrogen combustion. However, NOx emissions can be reduced even with hydrogen by continuing to lean out the fuel further. And as you can see from this graph right here, basically a total equivalence ratio is proportional to your air-fuel ratio, so a lower total equivalence ratio means leaner fuel. And we found that when you basically leaned out the fuel even further, at 30% hydrogen at this lower total equivalence ratio, you basically get the same NOx as at 0% hydrogen. So really, your NOx is dependent on how much air your engine is able to take in. Our engine was not able to take in a whole lot of air because it didn't have an upgraded turbo or high pressure fuel injection. So for these higher hydrogen blends, if NOx is going to be an issue, it is recommended to install something, again, like high pressure fuel injection or potentially a turbo upgrade to ensure that more air is able to get into this combustion chamber, really to ensure that when you're blending hydrogen, your NOx levels don't exceed what is actually able to be permitted for. So continuing down the emissions ladder, the reduction in CO2e does increase at 90% torque, coming in at about 11%. And the reason why we found that your reductions actually increase when your engine is at a lower power output is due to those increased volumes of methane slip when the engine power output is lower. When your engine power output is lower, your engine is basically self-limiting itself, meaning that a portion of the fuel, it's not operating at its peak efficiency, and a portion of the fuel is basically being let through, and rather than being combusted, simply being released to atmosphere. And this is something that hydrogen is really, really good at doing. It's what's known as a combustion promoter, meaning that it is very good at cleaning up any residual methane that's hiding in any of these engine pockets. And since methane is 25 times worse than CO2, your reduction in methane emissions will really start to have a greater impact on your CO2e at these lower engine torques. And at 80% torque, the trend continues. You're going to see about a 14% reduction in CO2e. And at 70% torque, really due to these very large volumes of methane slip that are mitigated through hydrogen combustion, you're going to see almost a 22% drop in your CO2e. And in addition to the emissions benefits, something we also found is that hydrogen is going to improve your combustion stability, which was measured by your location of peak pressure as well as coefficient of variance. So for this engine, your optimal location of peak pressure is around 18 degrees after top dead center. And we found that as the hydrogen percentage increased, you started to inch closer towards that optimal location of peak pressure, which is really defined as that crank position of each of the cylinders at the start of the power stroke. However, something that I'd like to add is it's really important that your location of peak pressure doesn't fall too far below this optimal operating point, as this could potentially result in a greater risk of misfire, which again could potentially damage the engine. So basically, the more hydrogen you add, the closer you're going to get to this optimal point. So basically, your combustion system designed for higher hydrogen blends may need to be retrofitted to potentially prevent misfire. And your coefficient of variance, which is really defined as how well the pressure curves for each cylinder are able to line up with each other, also ended up decreasing. So basically, especially at these lower engine torques where combustion may not be as stable. And the conclusion we came from that is that more stable combustion is going to reduce wear and tear on your engine equipment, which could potentially increase the time between maintenance intervals. So what are we looking at doing with these results? Well, based on the positive results of this test, and basically that we were able to prove out that hydrogen blending does in fact reduce combustion emissions, we are looking to utilize these results and move towards permanent installations of on-site production for fuel gas blending. So I mentioned pyrolysis earlier, and really the advantages of something like pyrolysis, which is kind of currently still in that lab stage, but is hoping to be commercialized within the next few years. It has that potential to eliminate the biggest pain point with blue hydrogen production, which is hydrogen produced from natural gas generally, which is the carbon capture piece. So, again, as I mentioned earlier, unlike current blue hydrogen production processes, pyrolysis does not rely on reformation, but it relies on thermal decomposition of natural gas, which, when performed in an oxygenless environment, as a byproduct, it produces solid carbon in either the form of graphene or carbon black, rather than CO2, which would then need to be captured and add to your overall project costs. And we're currently in the process of developing a project for a pilot pyrolysis reactor, which would then be blended to a to-be-installed newer gas-fired turbine that it will be made to be hydrogen capable at one of our compressor stations. And this is also advantageous because, as I mentioned earlier, the power requirements for pyrolysis are much less than something like electrolysis, while still having the same overall carbon intensity. And in addition, we are also looking at a potential waste heat recovery program within Williams to really evaluate locations where there is high potential for waste heat recovery to both offset our station load or potentially sell back to the grid to create an additional revenue driver. So in addition to looking at waste heat to power as well as waste heat to, again, offsetting our facility load to reduce our scope 2 emissions, one other usage case that we're looking at is using power produced from waste heat recovery to produce hydrogen from water via electrolysis, which would then again be blended back into the fuel to reduce emissions, very similar to what Enbridge is currently looking at. And while I will admit that this method is not the most efficient thermodynamically, the advantage with this is it does allow us to really create revenue through emission reduction through a number of these hydrogen production tax credits instated by the IRA, as well as allowing us to really build up a network of distributed production infrastructure at each of our compressor stations in preparation for large-scale hydrogen transmission networks. Getting away from the compression a little bit, just general hydrogen updates. Williams as a whole is a pipeline company, and as a result, there are a number of projects that would make use of our capabilities on that side and would either transport hydrogen through our existing pipeline infrastructure or focus on new purity lines that are completely separate from our natural gas infrastructure. So in addition to the considerations around embrittlement that I really previously discussed, since hydrogen is in fact less dense and less compressible than methane, really the effects on compression must be considered as well. And a research committee that I was a part of for PRCI, the Pipeline Research International Council, recently completed a desktop study really evaluating the effects of hydrogen on the integrity of all of our equipment at our compressor stations and other facilities besides the drivers themselves. And we were really able to determine that the three most vulnerable components that we really need to scrutinize under our pipeline blending evaluations are the coolers, the compressors, as well as any metering applications. So starting with the meters, most of our meters are gas chromatography meters, which are, if you're not familiar, we use meters to basically perform a gas composition analysis at our plant inlets and plant discharge. And gas chromatography is really the way gas chromatography works is it relies on a carrier gas to basically take a sample of your incoming gas stream, and this carrier gas basically pushes a sample of your gas stream into a heated reactor that's able to separate these gases based on thermal conductivities, and as a result is able to really determine to a high degree of accuracy what's actually in your gas stream. And in common circumstances, natural gas applications, your carrier gas is helium, due to it having a very different thermal conductivity than typical components in your natural gas stream. The issue with helium when you are blending hydrogen is that hydrogen and helium are so close on the periodic table and have very similar thermal conductivities that it's very difficult to distinguish between hydrogen and helium when metering. So as a result, in applications where we're looking at hydrogen blending, we do believe that it would be necessary to retrofit these gas chromatography meters by substituting the carrier gas with helium for something like argon or nitrogen, which are different enough from hydrogen that it wouldn't cause any errors in your measurement. Moving forward to the compressors, so our contracts, a company like Williams, our contracts, how a company like Williams makes money is we deliver a certain amount of decatherms of energy to our customers. Our revenues are not dependent on the volume of gas we delivered. It's really dependent on the energy. And since hydrogen is less dense and less compressible than methane, you're going to need to flow more of a blended product at a higher pressure ratio, meaning, because you have to flow more gas, because hydrogen is less compressible, and the operating pressures need to be higher. Your operating point is going to shift down, up and right when hydrogen is added, meaning that you are going to run at lower efficiencies and be much closer to kind of this stonewall point. So because of this, what we're finding is that under applications where we're looking at blending hydrogen, it's likely going to require things such as operating your engine, changing out your compressor body to, again, get to a more central point on that curve, potentially rebuilding the compressors to ensure that your pressure ratio and your inlet flow rates, again, are further away from the stonewall point as possible. Or if the blend percentage is high enough, we're going to need to do full engine replacements as well, or adding additional compression to accommodate those additional volumes. And third, one of these other key vulnerable components is our interstage and after coolers. Basically, what these coolers consist of is between stages of compression. Basically, these coolers are able to cool down the gas from the discharge temperature to typically around 120 degrees to ensure that it remains within the operating point of the compressors. So since hydrogen has what's known as a Joule-Thomson coefficient that is very close to zero, it's actually more difficult to cool than natural gas. And the fact that your pressure ratio is going to be higher when hydrogen is added, your discharge temperature is then going to be higher, meaning that your coolers may be undersized and may need additional cooling capacity to be able to kind of take in this hydrogen blend. So we've done some modeling on our coolers, again, for these blending projects that we're looking at. And the good news is that, in situations where the hydrogen concentration is below 5%, we found that our coolers, it still functions within the design capacity of our existing interstage and after coolers, indicating that uprates of our coolers are not going to be required, which is very promising. And with higher hydrogen blends, this likely will not be the case, but the good news is that for lower hydrogen blends, we're finding that our coolers are able to function with the same efficiency. So to conclude this presentation, really completing this test was Williams' first hydrogen project, and we learned a ton from it in terms of operating conditions, the effects of hydrogen on combustion, as well as safety precautions that we need to take for really any hydrogen project. And as you can see from this picture right here, there were many people, both internal and external, that were able to contribute to the success of this test. And if hydrogen is truly something that this industry is going to trend towards, it's going to take the collective knowledge of every single person in this room to really be able to bring us to that point. And however many years that takes, this is something that I do have the utmost confidence in, that the experts in this room will be able to get us to that point. So, thank you.
Thank you, Jacob. We have time for a few questions. Any questions? With the, I'm going to pronounce it wrong, pyrolysis, what kind of footprint are we talking about?
In terms of area?
Yeah.
Pretty small. It's, I would say, pyrolysis. So if you imagine an electrolyzer, it can fit within like a typical shipping container. Pyrolysis is very similar to that.
Any questions? We got one back here.
Thank you. Great presentation, Jacob.
Thank you.
I thought when you were mentioning the cooler issue at the end that you might also, I didn't know if y'all had looked at leakage out of your typical fin fan cooler at a compressor station, but I know for us at Kinder Morgan, it was a problem even with natural gas. Forget hydrogen. So just curious if you had any thoughts on that.
Yeah, so in terms of the leakage, so during our evaluations, we looked at integrity, capacity, as well as just effects on the leakage side itself. And you are absolutely right. Some of the components, specifically your wetted parts, potentially valves, as well as your components inside the coolers themselves. We are going to have to evaluate those for leaks, likely consulting with the manufacturer to determine, what precautions need to be taken. But really, we're at a very early stage with a lot of this stuff. We're trying to figure out if it's feasible from a technical perspective and won't require a completely new piece of equipment or large equipment retrofit. So proving that out was really the first step. Once these projects actually kind of move more into the development, go towards FID state, that is something that will have to be evaluated as well.
One more question?
I found your system concept with the pyrolysis and blending quite interesting, but if you mentioned it, I missed where you quantified what you're doing with that, how much CO2 reduction you're getting from that system concept.
So the pyrolysis project is meant to be more of a pilot proof of concept type thing. In terms of actual percentage, hydrogen blend percentage, it's going to be less than 5%. It's really meaning that your CO2 reduction from your hydrogen blending is going to be pretty much negligible. It's really more of a proof of concept kind of deal.
All right, thank you, Jacob.
Thank you.